clip 1, and we're starting in probability distributions. We're starting with discrete random variables, the standard sort of cut in half. Discrete just means particular values, usually whole numbers, and rather than continuous, which usually relates to measurement, which is all the values on a measurement scale. So when we're talking about discrete, particular numbers of amounts can occur. A probability distribution is just a summary of what the distribution looks like, what can happen, what its mean is, what its standard deviation is, and the ability to sort of calculate probabilities for events within it. So we'll start with an example. This is a good dice game. Roll 2 dice, add them together, and you win a prize if you get a 7. And so I've got the 7s down here. So the prize for getting a total of 7 is 3 out of 36, or 1/6. So there's nothing too dramatic here. But in terms of turning this into a probability distribution question, that starts now. So we make a definition that seems odd initially. We say x equals the probability distribution of the possible income for a player in this game. Now what I haven't made clear is if you roll a total of 7, you get a 10. If you, let's go back to the conditions of the game. You pay $2 to play. The payout is 12 if you win. If the total is 4 or less, you get your money back. Okay, so the probability of a total being 4 or less, there's 6 ways that can happen. Probability of winning, there's 6 ways that can happen out of 36. So here is the probability distribution of the possible income. 3 things can happen, so these are the possibilities. You can win $10. You can lose your $2. Or you can break even. For each of those 3 possibilities, we've got a probability that goes with them. Now the probability is based on the grid above, on the table above. And so that is a description of the probability distribution for the income in this case. Now, as we go on, there's a little bit of notation we've got to get used to, some of which may be familiar and others not. This is a sigma symbol, Greek letter, and it just means sum or add them up. X stands for all the possible values, so it's like the general term that stands for, in this case, 10, -2, and 0, all 3 of them. X, and often with a little subscript I, although I haven't done that in this case, maybe I should, stands for the individual values. And so when it says P for probability, that the actual distribution equals a particular value is how I would read that. And remember, these probabilities here, just like any other probability situation, they always have to sum to 1. And sometimes you'll be given a situation maybe where you've got to work some of them out, and the last one you never have to work out. You can just go 1 minus the one you know. So that's not a new principle at all, but it can be handy, and it's certainly worth keeping in mind. So when we're describing a random variable, the first thing is we've got a list of possibilities, and when it's discrete, those possibilities are 3 discrete specific values. Each of those values in this case comes with a probability of it occurring. And so the final part in describing it is mean and standard deviation. Now this is where the notation comes in, and this formula here and this formula here are given on the formula sheet. So we don't have to remember them, but we have to know what they mean. So E of x is called the expected value, but it's a mean or an average. On average over a large number, if this is how casinos survive, they work out the expected value over a large number of people playing the game. They know some people are going to win, but they know the odds. And so expected value is used in the gambling industry all the time, or they wouldn't stay afloat. It's the individual x values times their probability. Now this makes sense if you look at the table, because so basically it's the value times its probability. So 10 times 1/6 plus -2 times 4/6, that's your loss, plus and 0 times 1/6, which obviously isn't going to change much value, but it would be rude not to include the 0. So that's what we've got here. The expected winnings, the probability of each value times the value. And actually I've got it typed out there in the opposite order to the formula because it has the value first, then the probability. If you add them all up, you get this. Now, in context, that means on average, for every game that's played, you will win 33 cents. So that's good. That's a game you should play. Play it 100 times and you win. Your expected winnings would be $33. That won't necessarily happen for everyone, but it's an average. Now, the variance, and we got this, and this is maybe newish, but we've got this in relationship here, and this is one to commit to memory. Variance is the standard deviation squared. Now, they have an interesting relationship, and particularly in the standard, and this part of stats. The variance is easy to calculate, it's easy to manipulate and work with. The standard deviation is the one that makes sense in context. And if you think about normal distribution, which we will later in the topic, we've got a sense for that standard deviation given that average distance from the mean. Now, the formula provided is a slightly fancy looking one, but it's not as complicated as it looks. It's made up of two parts. The second part we'll look at first. The expected value squared, well, we've already got the expected value in this context, it's that 0.33. The expected value of x squared looks more mysterious than it is. Basically, in that case, if you think about the table, and sometimes I do it this way, sometimes I put another row on the table and say, well, 10 squared is 100, -2 squared is 4, 0 squared is 0. So basically these values get squared and then times by the probability is what the expected. And so that's what the expected part of x squared is there. So a 6 now times 10 squared plus, and so 4/6 times -2 squared and so on. Now that gives us 19.33. Then we combine them together, so 19.33 minus the 0.33 squared. Doesn't change it by much, 19.22. But we don't really care about the variance. 19.22 doesn't make any sense in the context of the spread of winnings. But if I square root it and get $4.38, you can see that our expected win on average per game is $3.33 with a standard deviation or an average difference from the mean of about $4.38. So that means most people, if they've played a few times, are going to win, somewhere between $4.50 and losing $4, something like that. Now, you can find both of those values on the graphics calculator. I'll add in an extra little clip just going over that using the stat end of the calculator, which we'll get quite familiar with by the end of this. And so on the bottom of the page of the note is a description of how to do that. And we will, when we're talking about a description of the distribution, x in general, all the possible values, the probability that goes with each value, some sort of central measure, so we call it expected value of x or the average, and some sort of measure of spread. Standard deviation is the most useful, but we're most likely going to calculate the variance using the formula and square rooting it to get the standard deviation. Okay, so that's part one.